Thank you very much. It's very nice to be here in Milwaukee. I am truly impressed and inspired by the energy that you're bringing from the corporate sector in particular to this issue. I think it's very much needed. I guess my job is black and blue. Is that the from carbon footprint to blue footprint? So I'll work through this. Let's see, I am at UC Santa Barbara. Am I getting feedback, or is that just from my son? This is what I want to try to cover. I want to start by going back 50 years or so and then thinking about looking forward 50 years. And I'm going to argue that we're in the process of a very exciting change, and we need to take advantage of that. I'll talk a bit about the climate challenge, but I'm going to presume that most of you have had Climate 101 and 102 and ad nauseum, so I'm not going to run you through all the basics on climate change. I would like to talk a little bit about a security angle that may be new to some of you. Talk a bit about water and energy, as the Senator mentioned, and then talk about building resilience and opportunities. Where am I supposed to point this thing? Oh, there we go. No, I went too fast. All right, so 50 years ago, let's look back first 50 years. This is jumping around on me, isn't it? So as I thought about this, I did some work with a major, I guess the major water, urban water utility in the country, and they wanted to look forward 50 years, so we started by looking back, and the more I thought about it, the more it brought issues to mind that I think are worth thinking about. 50 years ago, World War II had just ended. We were in a very, very different world at that point. What was good for GM was good for the country and the world. The Cold War was just ramping up. The Soviets were just moving ahead, actually, in the space race. Castro took power. China was in very deep trouble 50 years ago. U.S. economy was by far the dominant player in the world, and Los Angeles was the #1 ag county in the country. Very different world. Silicon Valley as well was agriculture. There we go. Importantly for our topic, oil was quite cheap in a relative sense, and nuclear was going to be too cheap to meter. This is very important from a water standpoint because my dad was a mechanical engineer. Thinking about limiting factors and constraints in engineering, energy just wasn't that big a deal. If you needed to pump it over mountains and use huge amounts of energy, that's okay. We're going to have plenty, and it was going to be inexpensive. You think about it, 50 years back, somewhere in the 1950s, this chart only goes 2005, so it's already out of date, but about 90% of all the oil has been consumed, and all of history has been consumed in that time frame. That's well within my lifetime and some of yours. That's an interesting plot, and it's interesting to contemplate how much longer will that persist. Water policy, likewise, in this era was a matter basically of just going out and getting some more. Whatever people demand, the agencies were expected to get it, and at low cost, high quality, and high reliability. This is a real plan. If I had a pointer, I'd point you to it. Take a look up at the water collection area up there in Alaska, and then you have the transfer region coming down the left coast there. Oregon and Washington won't need much. We'll send it right on down to the southwest and share some with Mexico. Of course, the Great Lakes were considered a wonderful opportunity to start putting in plumbing and moving that water to places that really need it. And here's the actual plumbing plan. This is only 50 years back. This is Parsons Engineering, and we actually did a serious engineering plan to replumb North America. We actually built small pieces of it. The California Water Project and some of the systems in the West are actually pieces of what was to be that master plan. Again, a supply-side thinking on the premise that there was plenty of water, essentially no limits, you just go further to get it, and energy was going to be cheap. It didn't quite work out that way. There we go. I'm going to return to that in just a second, but think about what then happened in a fairly short space of time. We put a man on the moon within a decade of that point, the Berlin Wall within 30 years, as well as the entire Soviet system would collapse. I actually was over there living in Eastern Europe for 2 years as the wall came down and then the system collapsed. Changes that I could not have imagined would occur in my lifetime, and they occurred peacefully. GM, this icon of industry, would actually go bankrupt in 50 years, and China would now own the largest share of U.S. debt. So the world has changed a great deal in 50 years. And sadly, on the 40th anniversary of Earth Day, that thing sank, and we're reminded of the vulnerability of some of our systems. We also have a little bit of a financial issue, and we can't pay for everything we'd like to see. And in fact, that is a change in the last 50 years. We had a different idea about infrastructure spending 50 years ago to what we now think about. And I'm going to argue that a lot more of the investment needs to occur at the end use side of the equation rather than that supply side of the equation that we were focusing on back then. Things that can't go on, Herb Stein says, forever, don't. And that, I think, is where I want to move us. So, looking ahead 50 years, and I think this is the opportunity. 3 parts of this as I started thinking about it. You need a vision. Where do you really want to be 50 years out? And in our case, in terms of water management, water use. To understand that, you understand first, where are you now? And this gets into everything from water meters and really understanding where do we use water now and energy for what purposes and how, and then figure out how do we get from here to there. So that's the new piece that I'm working on. And the more I look at it, the more I think it's kind of like this characterization. When you're right up against the bars, you don't tend to see the opportunities that are available. So we need to step back a little bit and think about what our opportunities are. Elements of this 50-year out vision, so profitable, productive businesses. It's perfectly appropriate for that to be right up at the top of the list. Entities that are solving problems, capital formation, livable communities, social equity, renewable energy base, and a net carbon negative system. What that means is pulling carbon out, getting beyond just carbon neutral, which we need to do, but if you really look at the science on climate change, what we need to do is pull back a bit. I think there are huge opportunities to actually do that. I think water's going to play an important role in that. So, the climate challenge. This thing has a funny lag to it. Okay. John Holdren, currently the head of the Office of Science and Technology Policy, the White House Science Advisor, former head of AAAS, physicist, one of the go-to people in terms of the science on climate change and energy in the world, certainly in the U.S. John noted that the world's already experiencing dangerous anthropogenic interference in the climate system. The question he says now is whether we can avoid catastrophic interference. You'll notice that dangerous anthropogenic interference is in subquotes. Does anyone know why? Anyone know what I'm quoting there? Legal scholars here. That's the language we agreed to in Rio in 1992, George Bush Sr. We are actually party to that. He signed it and Congress ratified the UN Framework Convention on Climate Change. So we are, at least in theory, supposed to be avoiding dangerous anthropogenic interference in the climate system. And what the White House Science Advisor is arguing is we've already failed at that. We're already in train. We really have a different challenge now. I'm just going to show you one chart, but one of the points here from the late 1800s to relatively current, I think I'm about a year back on this one now, is those green error bars are shrinking as we look at where we're headed with temperature and CO2 emissions. It's becoming more and more clear and more certain that we are heading into a warmer world. The Nobel laureate, Steve Chu, head of the Department of Energy, now says this is a real economic disaster in the making for our children. So some of the top folks in place now are taking this problem very seriously. But the question, of course, is what do we do about it? And I think that's the opportunity for the water sector. My own governor in California, who's in his last lap in the next 6 months or so in defending California's climate law, AB 32, said famously, the debate is over. And actually, from an administrative standpoint, that was very helpful. It moved California beyond a debate, is this an issue or not, to what do we need to do about it? And I think I would argue that's been very helpful. One of the big issues for California is snowpack. This is true in other parts of the world, and an increase in the elevation. That means it's going to go from snow to rain, all other things being equal. And these water impacts, that's the area, that's the watershed in the Central Valley and the area going down to zero snowpack. That one image from a colleague at Scripps and the modeling behind this became the #1 cause of action up through the U.S. Supreme Court on the tailpipe emission law. We have 2 major climate laws. California, it's the water impact that really captured people's imagination and caused the concern that carried the day in terms of our climate policy. Here's the precipitation forecast going out 100 years, and I put this up because there is a lot of uncertainty, not that climate change is happening, but exactly what it's going to mean in a given place in the world. And what this shows is it's definitely going to get wetter or drier in California. And that's actually a very frustrating graph for decision makers. They are looking for an answer. Is it going to get wetter or drier? I think actually this is very valuable information, though. If we're not sure, we need to develop robust, resilient strategies to deal with either future we may be looking at. And in fact, what appears most plausible is we're going to have wetter wets, drier dries, more oscillations and extremes in the system, and it's quite possible we're going to get wet periods and dry periods on and off. So it actually is valuable to know that we may get more extremes, but we don't know which way the signal's going. We better plan for both. That again ties into some of the issues here with water management. This is the #1 sentence, the opening point of AB 32, California's climate law. Global warming poses a serious threat to the economic well-being, public health, natural resources, and the environment of California. Again, that was the jumping off point for policy that is now being copied in other parts of the world and parts of this in federal policy. This is the little signing ceremony, and this is what we're doing in California, trying to get to 1990 levels by 2020, so we got 10 years to go, and that's the kind of reductions that we're looking at. There is a team that I'm part of that is implementing the water energy part of the policy for climate and water conservation, recycling, dealing with the energy intensity of water systems. I'll talk about that just in a moment. Urban runoff and stormwater reuse and renewable energy production. And can you see the top of that on your screen? I can't see it on this one. It's called the WETCAT. This is the acronym for this, so there's the cute logo that somebody produced for us. I want to now switch just a moment for a topic. How many are familiar with the Center for Naval Analysis and these two studies that have come out on climate and energy? Anybody run into these? A couple of you? There's the URLs. If you just Google CNA, Center for Naval Analysis in Washington, you'll get these two studies. They're free, available on the web, and I think well worth a look. This was interesting to me in a number of respects. I've dealt a lot with the climate science community and the environmental community and others, but the intelligence and defense community and their take on climate change and energy is quite interesting. Let me just give you a few quotes from, here's some of the people that are involved in this, just to give you a sense. It's not just the Navy, this is every branch of the services and very senior people who have run operations around the world on behalf of every single one of these. So here's some of the names. You probably will recognize some of those. What are these guys saying? Projected climate change poses a serious threat to America's national security, full stop. So the military and intel folks are taking this very seriously, but they're pushing specifically. Americans' approach to energy has placed the nation in a dangerous and untenable position. Given the national security threats of America's current energy posture, a major shift in energy policy and practice is required. Now, you might think what that means is go out and secure our access to foreign oil, for example. That's precisely what they think is not the thing to do. U.S. dependence on oil weakens international leverage, not foreign oil, oil. And I get into this in the study, and the reason that dependence on oil is a problem is because of the climate issue, that just getting it is not securing America's future because burning it is going to create the problem. U.S. dependence on fossil fuels, so they extend it to coal and in fact natural gas, undermines economic stability, which is critical to national security. U.S.'s outdated, fragile, and overtaxed national electric grid, dangerously weak link in national security. So fossil fuels generally, including coal, oil, and the grid, they see as a weakness. In terms of the grid, vulnerable to intentional or natural disruptions, and they bring in the water issue here, energy and water supplies at risk because of the grid's condition. So what do they argue we should do? Not just beef up the grid and beef up security of supplies of fossil fuels, but basically get off them. We need to shift off of fossil fuels and centralized systems, improve energy efficiency, reduce our dependence on oil quickly, shift from fossil fuels to renewables, and reduce reliance on the grid. Very interesting perspective coming from that particular group of folks. So how does that tie into water? I'm actually thinking that's going to be a lot of business opportunities for those 120 plus businesses that are right here in Milwaukee. This is total water withdrawals, just to get a sense of the picture. The mountains on the left, this is from USGS. They do about a 5-yearly study on water use in the United States. Most of that water use on the left is irrigation. Those mountains on the right, anybody know what those tend to be? Those are power plants. The biggest withdrawal of water in the United States is for thermal power production, slightly beyond agriculture now in the latest study. Now, a lot of that's returned, so this is water withdrawals, not water consumption, but that's a huge impact on water systems in the U.S. and around the world. Every major water supply system where I am working in California is over-allocated, but that's true in many other places. I'm working some in China and other parts of the world, serious problems of over-allocation of water. The comment was made, east of the Mississippi, west of the Mississippi, but you take a look at where we have the one large operating ocean desal plant in the United States, it's in Florida, not on the West Coast. We are looking at building some right now, and they're quite controversial. But there are serious water shortages in the southeast. Atlanta certainly went through a tough one. Been droughts and water shortages in New England. So we have water shortage issues all over. We need to reduce, according to the business community in Southern California, a very interesting statement, reliance on imported water to Southern California. And I'll get into why that makes a big difference. But the interesting upside opportunity is local supplies hold much more promise than people realize, and the business community has been out front and talking about that. Here's the new water supplies for California, and I show a couple of California points just to show some of our mistakes, frankly. But if you take a look at this, is the formal California State Water Plan is consistent with the last one that was 5 years ago. Just look at the bottom 3 bars on that. The biggest new water supply in California in the next couple decades, this is per year, is going to be urban water use efficiency, just cleaning up the waste in the urban system, plumbing fixtures, irrigation, leaks, and so forth. Next is groundwater systems, and a lot of that can be stormwater management and capture, and then recycled water. And most of us think those are probably all conservative bars. They're probably going to be even stronger than that. The relative numbers are what are important. If you look at surface storage, and the dark blue is what's fairly certain, that's the one we love to fight over. We just pulled an $11 billion bond off the November ballot because it was clearly doomed. And most of that fight was over the small blue bar there. So very contentious building surface storage, and you really don't get that much relative to what everybody pretty much agrees to is let's clean up the waste. And you go on up through the other sources. Now I'm going to tie that into energy and why that's important in terms of climate. So here's quickly some comments on the energy link to water. Every time I go for there we go. So here's the steps. This is a little methodology I developed for the Lawrence Berkeley lab about a decade ago, and that's what we've used in the U.S. Or the California component, and the Canadian government's also adopted this basic approach. You start with a source of water, and you first have extraction and conveyance. You pump it out of a lake, a groundwater source, a river. You move it from point A to point B, then you treat it. And then you have energy often in distribution, not always. There are places where you can skip these boxes. Then you have a lot of energy in the end-use box for whatever the purpose is. In a building like this, we have circulation pumps, heating, cooling, additional treatment. Wastewater collection. Wastewater doesn't all flow naturally to exactly where we want it. We actually have to pump it around. Wastewater treatment, most of the energy there is actually pumping air, not water, but there is some water pumping as well. And then we discharge it, and there's actually pumping for discharge. Or we go to the inside loop. Once we've already treated to legal discharge requirements, there are opportunities to reuse water. And so there is anywhere from 0 to a modest amount of energy for treatment to take it another step, and distribution to be able to go that inside loop. One of the interesting opportunities is looking at the difference between all of those first couple of boxes versus the recycled boxes. And in many cases, it's a lot less energy to recycle water than to throw it away, go get some new, and bring it in and use it. Many of you have heard these figures in California. I was involved in the group with the California Energy Commission that developed these estimates. They're rough estimates, but I think they're roughly right. About 19% of electricity, all electricity in California goes to the water cycle. That's to all of those boxes, not just the conveyance. And about a third of the non-power plant natural gas. That's a huge amount of energy. One of those tricks is when you do begin to measure things, you can manage them. And we are actually catching up in terms of understanding what we need to manage in the way of water and getting energy benefits and in turn greenhouse gas emission benefits from improvements in the water cycle. That's both efficiency and source switching, going from potable water to, for example, recycled water or rainwater harvesting. Here's one example, all the pumping plants on the California system. This is the largest single user of electricity in California, the state water system. Here's all the arithmetic that goes behind it as we add up all the pumping, including energy recovery on the downhill side, so that becomes a credit. And the point of all that is to do a little comparison here. There we are. This is the energy intensity in kilowatt hours per acre feet. And the point is just the relative amounts. All the way on the right is several different estimates on ocean desal. The middle one is probably the most accurate right now in terms of where we think we're headed, but we don't have operating plants at scale right now, but about 4.4. It's a figure that I developed for the governor's task force, but somewhere in that yellow bar noise. Take a look at the red ones. Those are all the import schemes, and that's raw water. So I haven't corrected for the additional energy for treatment, but that's the Colorado River Aqueduct, the smallest at about 2,000, all the way up to over 5,000 kilowatt hours per acre foot for some of the terminus points on the State Water Project. So already more energy intensive than ocean desal right now in our system. Then you look at the real bargains over on the left. You've got the green ones with groundwater, even groundwater using reverse osmosis to deal with salts and nitrates that's currently being served up as potable, high-quality potable water supply after treatment using reverse osmosis. And wastewater treatment, including wastewater treatment with RO for various reuse purposes. All of those, from an energy standpoint, are a huge bargain compared to what we consider the business as usual case. And then efficiency I'm showing at 0. Some have argued I should make it a negative number, but basically if you fix the leaks, replace the plumbing, clean up the systems, that doesn't take any unit energy for the opportunity. Now, as I said, efficiency, being the #1 new supply of water for California, is down there at that 0 bar in terms of energy intensity and emissions. That's what our RO system looks like if and you haven't seen the technology for reverse osmosis. This is the same technology with slight variations used for ocean desal, brackish water desal, wastewater, and so forth. There we go. So just back to that bar again. So if you look at that bottom one, that's at 0 energy, getting huge new water supplies. Groundwater, a very good bargain and recycled. So the point is, by going to the best buys, but that's going to take technology and a lot of what your companies are offering, that's going to give us huge emission benefits and energy benefits. So quickly, some policy responses here, how to deal with this. There we go. This is a statement issued by something called the California Environmental Dialogue. It's a group of little family-owned companies like Chevron and Bank of America and BP with environmental organizations, state agencies, and others, and they came up with a very strong validation of basically the common sense approach, the step aside from a lot of the controversial supply side water approaches. Let's get on with the efficiency, the recycling, and so forth. I think that's important because the business voices carry a lot more weight than some people realize, especially combined with the environmental voices in the public policy process to say, let's do the sensible things first and get going on those. Let's quit fighting over these. Some of the key elements to be integrated when we talk about integrated water management, it's much more than just integrating several different sources. It's water supply reliability and quality, it's energy, security factors, economics, environmental restoration. I put in the restoration because we have some healing to do, and then sustaining those systems, building resilience in systems, and tapping multiple benefits. And those multiple benefits are in all the categories above. So we have benefits that are economic, environmental, social, and so forth. Some of the attributes in building these portfolios for a different water future, technologies and prospects for improvements. I think there's huge upside potential for technology improvements. Energy intensity of systems. We have lots of opportunities to reduce the energy intensity. Treatment requirements and options. We know that treatment requirements are going to continue to increase with concerns over various pollutants. That's a challenge. We need to take it on. Source and system reliability, vulnerability and resilience, and economics. There we go. So, you were all aware of a lot of the pieces, but some of them are quite simple. Actually, it was interesting to find that a lot of X-ray machines, a lot of lasers use once-through cooling technology still. What that means is basically potable water treated, brought to a facility, and just continually cycling through for cooling. So huge water use efficiency gains just by going to recirc systems on some of those technologies. A lot of it's outdoors, depending on the climate zone, on the order of half and half, indoor, outdoor, lots of opportunities to plant the right things, irrigate them intelligently, and get a big water savings. And then a lot with recycled water opportunities. Right now in California, we recycle about 10% of the opportunity and 90% flows to saltwater sinks. But by using more water in recycle mode, we're able to then extract less out of systems and pull back on the impacts of some of the systems that are in jeopardy. One of the big ones, though, is we're just running some numbers now in California. We're way behind other states dealing with stormwater management, rainwater harvesting, getting water to recharge aquifers. This is our sophisticated system in Southern California. When it rains, we have this. And this is partly why. This is one area in Southern California. This is the Santa Ana watershed. This is above Disneyland, if you know that area. Was mostly agriculture. I won't go through the whole key, but most of the red is the urban. That's what you need to know. 1933, then we move along in time, get up to the 90s, and it's almost all paved over, which is why when it does rain, it all ends up just washing everything. The loading factor, in fact, we have the world's largest concentration at the time, 350,000 dairy cows down in the lower green part. That's the bottom of the watershed. Not a good thing when that's all mobilized and picks all that up. Orange County didn't appreciate it, so they sued. So we're dealing with trying to infiltrate groundwater. The traditional way is to build big ponds. This is the we're finally getting it approach, which is landscaping paved surfaces either to be permeable directly or into these vegetated swales. So here's just a couple of images of this, the kind of rediscovery of how to handle rainwater. Rainwater garden in a commercial area. These turn out to be extremely effective. I don't know why this is bouncing on me now. Okay, this is a green roof, and you see these all over the world. The major buildings right now in Tokyo, Japan, are all required to have cisterns and green roofs at this point, the biggest buildings in the city. So you think of it as small scale, a small building like this. This is in Southern California, but you're seeing this in Washington, D.C., Detroit, all over the world, actually, big in Germany, going with these green roofs and then capture. I ran numbers with the Natural Resources Defense Council last year on what this might mean for California, urban Southern California and urban San Francisco Bay Area. It turns out, I won't bore you with all the numbers, but as we ran through it, we could save or pick up hundreds of thousands of acre-feet of water using water harvesting after excluding all contaminated zones, on and on, industrial zones. Not that you would need to do that, but just to be conservative, we did that. And ran through the geology, the aquifers, and so forth. Huge amounts of water that could be captured and beneficially used in Southern California and Northern California, and translated that into the energy savings, including the energy it takes to pump it and treat it, but comparing that then to what the alternative would have been in terms of importing or ocean desal, and then the greenhouse gas emission savings. And this is actually one of our measures now for dealing with greenhouse gas emission reductions in California to capture and reuse rainwater, because it actually makes that much difference. So a few observations on water, and then I'll close. Water is infinitely renewable, but it's limited in space and time. It is a finite resource. And it's very low in substitutability. There's not much else you can water crops with, but it's very high in demand elasticity. If it gets more expensive, people do change behavior and use patterns. Longage versus shortage. There always will be a shortage of cheap water. Another way to say that is there's a longage of demand, and that's beginning to dawn on policymakers in different places that will never solve the problem if the resource is undervalued. It's got to be valued in a market sense, in an economic sense, somewhere close to reality. Undervalued resources cause a misallocation, and we're always then going to be underinvesting in efficiency improvements if it's too cheap. That doesn't argue for a lack of concern for equity, though, that it is possible to use even subsidized lifeline rates for an essential amount of water and then bump your way up. And so those increased tiered rate structures are a very good way to solve for both the economic return that's required and social equity. Local sources versus imported water. A lot of our thinking, as my North American replumbing diagrams show, a lot of the thinking has been on go import water from somewhere. And most of the thinking now is use local water supplies. And you think about it, when it has to be treated to higher and higher quality levels, that actually advantages local sources. If you've got local groundwater and it does have some issues, but it's still treatable and usable, and the alternative is import water for somewhere else or go for more expensive sources, and then you still have to treat it, you're actually advantaging local sources. That's going to change some of the water dynamic, I think, in terms of local versus imported. That also leads to diseconomies of scale. That is, that there are diseconomies to large systems relative to small systems in many places in the world, and that, I think, creates a business opportunity. That means a bigger isn't always better or more optimal. And you deal with some of the sunk capital problems, that is, having to invest very large amounts of resources and capital for systems and then have to deal with amortizing that over a long period of time. We can break it into smaller bite-sized pieces. Technology improvements mainly are at the end-use side. We're not seeing vast new advances, to my knowledge, in dam building and major conveyance systems, but we're seeing huge and dramatic increases in opportunities through technology for water use efficiency, measurement, control, filtration, and so forth. And a lot of those, again, lead to decentralized advantage, end-use advantage, and local supply advantage. So, my stirring conclusions here. In 1990, about 20 years ago, Roger Revelle and Paul Wagon are two of the senior figures in the climate science world. This is Commander Revelle, the one that actually got Keeling to go to measure the CO2 in Mauna Loa at Scripps Institute. These guys said, they're scientists, 20 years ago, governments at all levels should reevaluate legal, technical, and economic procedures for managing water resources in the light of climate changes that are highly likely. I'm intrigued that they zeroed in on the legal, technical, and economic procedures. Most people are thinking build bigger levees, build seawalls, and so forth. They were realizing 20 years back, we need to rethink our institutions, and I think that's exactly right. We need to integrate planning for water, energy, climate change, the economy, and the environment, all in one package. And we need to really think about tapping into local opportunities to build the resilience that we're going to need. So let me close with one of my favorite Winston Churchill quotes: people and nations behave wisely once they've exhausted all other alternatives. And it does seem to me that that's kind of where we are. So thank you. I don't know, do you want to do questions now, or yeah? Do we have time? Okay. Yes, sir.
Given your core theme of more efficient ways of managing water and energy, and considering what you know about the Milwaukee region and its assets, any suggestions on how to further capitalize on focusing in that area of recycling? Is there any particular area that Milwaukee should continue to retool on in that regard?
You know, I don't know Milwaukee well enough to really comment on what you might do here, and I know you have a lot of water capacity in the system in the city itself because of the shifts in industry and brewing and so forth. The technologies to measure and manage water, and it sounds like a lot of the firms that you were talking about in your opening comment that have to do with control technologies, understanding constituents, filtration technologies, monitoring. I think that's where the action's going to be, and every one of those involves efficiency improvement steps that are going to be valuable from an economic standpoint. So I'm not sure there's one answer. It's probably lots of small pieces that really do add up. So that's probably where I'd leave it. I think, we think about the issues of recycled water. I just did a talk last week for the Public Utilities Commission in San Francisco. San Francisco gets its water from a national park, Yosemite National Park, quite controversial 100 years ago with John Muir and the rest. And they consider it a very exciting thing to have this hetchy water from a national park. And it's already recycled water. Great to their upset. They didn't realize there is a wastewater treatment plant in Tuolumne Meadows in the high country for all the tourists that go through, if you've ever visited the high country. And that water is treated to high quality levels, put back in the river, and so they're already drinking recycled water in San Francisco. They didn't know that. And frankly, that's true of basically all of our water supplies all over the world. It's very rare that you get a system that isn't somehow already recycled water. The question is, how do we do it well? How do we safeguard public health? It's not whether or not to do it, it's how to do it well, and that's the challenge. Great, I answered every other question. All right, thank you.